We got the recording going now, so speak now or forever hold your peace. No, I'm sorry, that's a different thing. We don't have to do that here. Hey, I did it once.
I've done it twice.
Okay, well, it's okay. So all this week and part of last week, we've been talking about systems problems. This is week 7 of algebra. And so we have 2 more weeks to go. Next week, we will be doing the test for this unit, which is unit 3. So that is the last of the 3 unit tests that we have. And then the following week after the race and Memorial Day weekend will be the final. So the last week after Memorial Day weekend, it probably will not have direct instruction classes, but I'll still hold the Zoom session. So if you got questions, you need extra help, you can come on and do those. So I'll be here and available, but you don't necessarily have to come into class or have to go to the Zoom. Not next week, the following week. Because the week of June 1st, because that week, the end of that week, I have to have grades in on a Friday. So if you've been in Google Classroom this morning, hopefully you saw the notification about having all assignments completed by that Thursday, June 3rd. And that's coming up here in 2 weeks from today, actually. So remember, 80% of your grade is from the tests. So concentrate on doing well on those tests. If it means you don't have time to do a homework assignment, you know, that's just the luck of the draw. So make sure that you do enough of those assignments to be ready for the tests, or get help or get feedback from me on them if you're still struggling with something. Questions, anybody, about any of that? All right.
How many times do you take the final?
Once. You get to take the final once. You can take the other unit test as many as 2 times, because I have 2 different versions of that. The final is only 10% of your grade.
Oh yeah.
So if you're borderline between, say, a B and a C or an A and a B, doing well on the final will put you over, but it's not going to, significantly affect your grade. The 3 unit tests are 80%. That's the biggie.
So if you have if you have like a 60.75, do you still pass, or does it?
That would round to 61.
Okay, good.
60 or above is still passing. Below 60 is an incomplete. I'm going to give everybody every possible chance to pass this class, because I know how important it is. And you need to have some, feeling of progress. So let's get it done. Get through this stuff here in the last 2 weeks. Don't, if you're a procrastinator, now's the time to get busy, because you won't have much time to procrastinate anymore after this week. So systems, graphing, elimination, substitution. Jessica asked me about, do we have to use substitution if the problem says it? Like, no, not necessarily. We're gonna shift here to something else that I know Kathy's gonna especially love: word problems. I'm glad you're chuckling about that.
I hate them.
I know. I usually joke that it's everyone's favorite, because I know that it's no one's favorite. So I already spoiled that today. I can't use that joke today, so that's okay. The word problems, you might be surprised that these aren't that bad, because we're still talking about systems. And so what is our best way for equations to be written in systems? Well, hopefully they're all going to be in standard form so we can do elimination, right? In the columns, AX plus BY equals C. And you'll see these word problems are generally set up to do that, although there's some that you could do substitution on if you really like substitution. So the only difference here is that now you're putting something behind these equations that connect to some real life situation or theoretical situation. And this third bullet point is still the important part of all this. You know, you guys need to be able to determine whether or not you should graph your solution, whether you should use substitution or elimination. And the end result's going to be the same for these, just like it is when all these other systems problems. You only got 3 possible outcomes. You got one solution, you got no solution, or you have infinite solutions. Okay. Oops. Slope intercept is great if you have a y equals mx plus b situation. Remember the simple, the first word problems that we did, like that electrician word problem, you got a variable plus a constant equals a total. And the dog losing weight, you got a variable plus a constant equals a total. That's a good setup for slope intercept. Standard form, though, works best anytime we've got multiple unknowns and we just need to set them up so that we can do our elimination in the columns. Get those cancellations put in place. So here's a pretty typical example of a word problem that could represent a system situation. We got 2 Excel Center locations. They got trips to an indoor climbing gym. Michigan Street students rented and filled 7 vans and 9 buses with 267 students. Okay, and the Meadows students, 9 vans, 9 buses, 279 students. And so it says how many students can each van or bus carry? And the vans and the buses are going to carry the same number of students. So looks like a lot of different numbers there. Anybody want to take a swing at how to set up at least one of these equations? Okay, don't everybody try it once.
So do you start dividing 267?
Got to set it up first. This is a systems problem.
Okay, so would you use standard form or would you use the slope intercept?
How many variables do we have?
I don't know. You share your screen again and let me look again.
We got vans and buses. We got vans and buses.
Okay, so two. Yeah. 2 variables. Okay.
Right. Jessica, what did you start to say? Okay. Jessica here in class picked the second one, the Meadows, and said 9x plus 9y equals 279. That's a good setup. My only suggestion is in a problem like this, in a word problem, if you use x and y, now you got to remember, okay, what does x really refer to? Is it the vans or is it the buses? So I would use V and B. Yeah, van, V for van, B for buses, right? So one minor little modification, 9 vans plus 9 buses equals 279. That's the second one. That's just the one she started off with. The other one followed the same pattern. And if you notice, it is kind of looking like AX plus BY equals C. Oh, he's hungry. He needs to go out or something.
No, he's just annoying.
Oh, okay.
Nobody can walk down the sidewalk without him sounding the alarm.
Good dog. Well, look at this. You're solving the problem already, Jessica. She says, couldn't we just cancel out the 9Bs? Well, yeah. How you going to do that, though? Remember? We got to subtract the whole row. Changes all the signs. And you're absolutely right. The 9Bs will cancel. 9 minus 7 gives us 2 vans. Whoops, not the at sign, 2 vans. 279 minus 267 equals 12. Okay, easy enough. Vans are going to carry 6 students. Now we know what one of the answers is. We know how many students can go in a van. Then you take it and plug it back in. Let's use the second one because the numbers are lower. 7 times 6. I'm plugging that 6 in for the V, plus 9B equals 267. So it's my favorite number, 42. We're going to subtract that. So 9B equals 225. Yeah. So how many times does 9 go into 225? Huh, I should have known that already. 25 people per bus, 25 students per bus. That makes sense? Any questions about how I came up with that?
So you carried down, I know where the negative 42 came from because that's 7 times 6. But why didn't you bring it down to the 9B equals 225?
Because it was 42 minus 42.
Oh, yeah.
I canceled. I canceled it. I already know 7 times 6 is 42, so I'm just jumping right to its opposite. The opposite of positive 42 there is negative 42. So it's gone after that row. It won't carry down into the problem any further.
Okay, I see. I didn't see the negative 40 or the minus. Yeah, negative 40 would be off to the right.
And believe it or not, that's a fairly typical word problem for these systems deals. It's not that bad. Well, I don't know. I don't think it's that bad, but you guys probably would disagree, and that's okay. So, questions so far? All right, let's see what other gems we have here. And there's the questions that we were trying to answer, and we did answer them. Focus question number 2, probably the most popular kind of systems word problem the Excel Center has. Lots of examples involving ticket sales because, you know, what school doesn't have fundraisers and ticket sales for stuff? You know, in this case, we got a school play, we got adult tickets, we got children's tickets. First day they sold a certain number, took in some money. Second day they took in some money, still selling adult and child tickets. And so we're trying to figure out what the price of one adult ticket and one child ticket is. So again, if you want to use X and Y for the variables, you can. I've found that harder to keep track of though, because you've got to make a note somewhere that, hey, the A actually, or the X actually refers to adults and the Y refers to children. Why not just use the A and the C to begin with? So you guys ready to tackle one of these on your own? Okay, doesn't sound like it. Okay, 12 adults plus 4 children equal 104. 11 adults and 4 children equals 97. Simple enough. It's going to be just like the last one. You got a cancellation that's already set up for you. 12 adults and 4 children's tickets the first day, and they got $104. 11 adults, 4 more children's tickets the second day, and they took in $97. We can do the same thing here as we did on the other one. We got, remember the 2 things that we're looking for on these systems problems is we want to find an elimination if we can where we've got the same coefficient and opposite signs. Well, we don't have opposite signs here, but we definitely have the same coefficient here on the children's ticket terms. So we do the same thing, subtract that whole second row. This one actually comes out a little easier because 12 minus 11 is 1A. Do I need the 1? Nope, you're right, I don't. 104 minus 97? $7. So an adult ticket is $7. So how much is a children's ticket? Again, I'll use the second one just because the adult number is a little bit lower and it's a double number. I love double number multiplication because it's easy. 11 times 7, 77. Right, $77 for the adult tickets plus 4 children's tickets equals 97. How much you get now for the children's ticket? You're wondering where that 77 comes from. Well, the adult tickets, they sold 7 on the second day. All I did was just jump right into the substitution of the value that we got for the adult tickets. That's good. The children's tickets should be cheaper than the adult tickets. Anybody out there got this one solved? How do you know? What answer you got? 16. No, 16 is not right for sure. Did you subtract 77 from both sides? And what did you get? 4C equals 20. Well, how'd you get 16 out of that? Why'd you subtract? That's not the opposite operation. 4C is 4 times C. Opposite, opposite, opposite. You got to be sure you pick the correct opposite operation. It's not 4 plus C. If it was 4 plus C, then I'd say, yeah, you're going to subtract 4.
So I worked it up until that point, but then I just did the wrong operation.
Yeah. You just got to, and that's why a lot of times you heard me say or ask, what's the existing, what is the operation now? So if you can get that in your mind, what's the operation that I'm working with? That should be hopefully a clue to tell you what the opposite should be.
Okay, so then the answer is
$5, right? There you go. Not 16. And I know you're wondering, since you heard me probably say that the adult tickets are more expensive than the children's tickets, and here you came up with $16 for.
I was like, wait a minute.
Yeah.
Yep.
That's all right. You're doing it. You're working it. This is that opposite operation. I know a lot of people struggle with this. I take away 77. That's the opposite of a positive 77. Leaves me with 4 times C equals 20. And then once you divide both sides by 4, you get $5 for the children's ticket.
And I remember the vehicle out the 4 or the 4.
But we got to divide. It's a division problem. Existing, it's multiplication. So we got to divide. When there's no space between our coefficient and the variable, it is multiplication. Questions, anybody? And we're on a roll now. All right. Got those figured out. Oh boy. This is one of my favorite systems problems. You're going to hate it. Not because it's one of my favorites, but because it doesn't look like there's enough information. Yeah, that's good. A nickel is 5 cents. Penny is 1 cent. Okay, we got one answer already without even doing the problem. 4 nickels and 20 pennies has been suggested. That would give you 40 cents. Okay, we got nickels and pennies equals 40 cents. Oops, nope, 0.40. So that's the coins that we have. But I got the wrong number there. That should be 20. You got 20 total coins. So you can't have 4 nickels and 20 pennies, because that's more than 20. You only have 20 coins in total.
Oh.
So that's why I started with this first equation. That's just the kind of coins that we have and how many coins there are. The second equation, now I can do the value. Nickels are 5 cents. I did it again, not greater than. Nickels are 5 cents. Pennies are 1 cent. And those are going to total 40 cents. Now, you're probably not like me in this sense, but I don't like having mixed terms like this, where I got whole numbers in one part of the problem and decimals in the other. So what can I do to get rid of those decimals in the second equation?
Subtract the O1P?
No, not subtract. We're not ready for that. I'm just talking about the second equation. How do I subtract 40 cents from 20 coins? We don't have the same thing. The first equation is in coins. The second equation is in dollars, is in monetary value. Jessica's got the right idea. Change this to 5. Change this to 1. Change this to 40.
Move the decimal point.
Move the decimal, exactly right. And all that really means is we're multiplying all the terms by 100. So 100 times everything in there. And if you remember how multiplying in decimals work, it moves, when we multiply, we're moving the decimal to the right. So now we got 5n plus p. I don't need the 1 anymore. It was 1p. And that's now totaling 40. Okay, good. Got rid of the decimals. I'm really glad to hear that you guys recognize that the need to do that, or at least knew how to do that. Because now we've got, this problem is exactly like the others. We've got a single p in each one of these. We can subtract this whole second row if we want to, or the first row. It doesn't matter which one you want to subtract. So the p's are going to cancel, right? This p cancels now with this p, because it's now, this becomes a negative p, right? And positive p. So then we end up with negative 4n. And this becomes negative 40 and positive 20, so negative 20. So how many nickels do we have? 5. Good. I was hoping somebody would chime in there on that. This is multiplication here, negative 4 times n. I never worry about negative numbers or negative variables in this problem, this kind of problem, because I know we're going to clean it up at the end when we do the division. So we got 5 nickels. How many pennies do we have then? Well, go back to the first equation. That's the simple one. No, we got 20 total coins. We got 5 nickels. And how many pennies? Subtract 5. Now we can subtract. Yep. So does that equal 40 cents? 5 nickels is 25 cents. 15 pennies is 15 cents. Yep, we got the 40 cents. Questions?
I have a question.
Good.
So okay, so I see where you subtract the pennies, but you subtracted from the nickels to get 4 nickels, or did you subtract from? Because I'm not understanding how you went from 5 nickels to 4 nickels. Was that subtracting the pennies?
No. Right here. I start off with 1n in the first equation.
Oh, okay. I didn't line them up. Okay. All right. Thank you.
Well, check those columns. And you know what? Sometimes if I had more room, a lot of times what I like to do, if I'm going to rewrite something, I'll pull it over to the side and then rewrite the other one also. So then, you know, if it makes more sense, let's do it with text.
Yeah, I didn't rewrite. When I rewrote it, I did not include the first. So I was only working off the rewrite.
It's all right. So if you rewrote it, it might look like this.
Yes. Mine did not because I didn't do it right.
Got that
Okay.
first row. Yeah, there we go.
Yeah. Okay. Thank you.
No, it's not 0.40 anymore. It's actually 40. And that should be negative. Once I subtracted everything, it should be negative. There we go. Signs, signs, signs. Everywhere signs. It was a great song by that band in the 70s called Signs. Blocking out the scenery, breaking my mind. I'll have to play that for you sometime. There's actually a video that's good on that. Any other questions?
So were you a hippie in your youth?
You just have to spit on me.
I kind of lived in a lot of different worlds. I was an athlete and went to an inner city high school, kind of did a little bit of everything. So I'm a child of the 70s. I can't escape that. I was graduated from high school in 1975. So yeah, oh, thank you. 9 years before you were born. Okay.
You are the same age as my oldest brother.
Okay. So I don't know what that necessarily will tell you about me, but you know, I grew up by Butler University, went to Shortridge High School. I was the only white guy on my high school basketball team. So it was interesting.
Yeah, we used to sled down Butler Hill.
Oh yeah, I've lived a block away from there.
Wow.
We broke up a lot of sleds and burned them on that hill over the years.
Yeah. Yeah. My mom had to set quite a few sprains and broken going down that hill.
Yeah, you had to watch out for people like me on the sleds trying to intentionally crash people. I'm a preacher's kid too, so if that tells you anything about why I do stuff like that, that's true. We are
Cops, yeah, cops' kids and the preacher's kids were the worst.
Yeah,
the worst.
I'm not going to deny it. I had fun though. Okay, so 3 problems now. We'll see if we got another one. This is another one of my favorites. Can you figure this one out? There's almost no information here. Find the value of 2 numbers if their sum is 25 and their difference is 1. Sum is the total and the difference is 1.
24 plus 1 and then 26 minus 1.
Yeah, but the difference is not 1 between those 2 numbers. Difference meaning subtract. Right?
Would it be 12 and 13? Or am
12
I
and
not
13. Yeah, that's exactly right.
Oh my God, I can't even believe it.
Good job. You figured that out just by looking at it, huh? Very few people have done that. And this is probably one of those that probably does make sense to use X and Y. X plus Y equals 25. X minus Y, here's the difference, equals 1. Okay, it's already set up to eliminate. You got a sum, which is addition in one problem. You got a difference, which is subtraction in the other. So 2x equals 26. One number is 13. So then if the difference is 1, the other number has to be 12 because those are the only 2 numbers that will add to 25. Not sure how you came up with that, Kathy, without working the problem out, but that's pretty good problem solving.
I just basic math. So because I was like, okay, 12 plus 12 is 24, but that's not, that would have been 3 because it would have been 12 plus 12, 24 plus 1.
Yeah. I mean, if you think about all the possible numbers that can add together to be 25, if you just put them in a list, there's only 2 that have a difference of 1 that still add to 25.
All right.
And it has to be, I mean, this is one of these problems that doesn't necessarily have to be solved mathematically. You could figure it out just by logic or making a list. Well, a lot of people still struggle with it though, because it is set up to do as elimination. 2 doesn't go into 25. That's right. But I'm not, these are added. These are added. The y's are subtracted. The y's cancel. Got a plus and a minus y.
After I said that, I looked up, I thought, wait a minute, there's where you get the 26.
These are, some of these are kind of brain teaser, almost like riddle type problems.
Yeah, I don't like critical thinking. I just want to see it and get done with it. I don't want to have to, I just don't want to get that deep into it. I think that's how come I just don't want to read or try to figure it out. I know a lot of it is just regular multiplication, division, addition, subtraction. I just don't want to read through. I think I'm just lazy, I guess. I don't know, but I don't know.
Okay, focus question number 5. This one's a little bit different. And if you read to the very end, it says write an equation for each car repair shop using Y for the total cost and X to represent hours. So the goal of a problem like this would be to figure out at what point do these shops, these repair shops, cost the same amount, or is one eventually going to be cheaper than the other? Okay. The equation writing part of it is just like writing slope intercept. If you notice in the second row here, second line says $50 an hour. That's a variable right there. Because we're trying to figure out, part of this is figuring out how many hours are involved, potentially. And there's a $60 charge here in the third row just to diagnose the problem. So that's a constant, right? Roll the car in the garage, $60 right off the bat, just to look at it. $50 per hour for anything after that. Now, Bob's place charges $100 to diagnose the problem. So he's a little bit more upfront, but it's less per hour. So it says after solving, after how many hours would the repair for your car cost the same? So think about how you might solve that. I want to pause this for a recording for a minute. You're right, it is slope intercept. So far, all we've done are elimination problems. Remember when we started doing substitution problems? What was the format of most of those equations? Well, that's elimination. Look at your substitution sheet you're asking me about before.
Is substitution where you use 0 to solve for, use 0 as y to solve for x and 0 for x to solve for y?
That is the kind of substitution you would do if we were looking for the intercepts, yes.
Intercept, okay. All
yeah.
right.
But in effect, we kind of have the intercepts here. You know, I'll show you what I mean. This is one of those problems that really is truly set up to do by substitution. So if I'm using slope intercept, here's the first one, 50x plus 60. That's the first guy's shop cost. The second guy, y equals 40x plus 100. I don't know if you remember that from that one substitution handout where we had some problems where we had two equations that were both equal to y and how we set those up to solve. If I take this space out of here, so you put it back, no, equal. They're both of these things. This is my 50 cents, 5 dimes, 10 nickels, 2 quarters, 50 pennies. All of those things equal 50 cents. So here we've got two equations that are both equal to y. So we can make them equal to each other. 50x plus 60 equals 40x plus 100. That's a substitution problem that now we have created, and we've gotten down to one variable. So basically I took this 50x plus 60 and substituted it in here for the second y. I could have done it the other way. I mean, it doesn't matter because it says they're both equal to y. This is an age-old mathematical equation. If A equals B and B equals C, then A equals C. 50 cents, 5 dimes, 10 nickels, 50 pennies, 2 quarters. They all equal 50 cents. They all equal each other. That's why we can substitute. Now, I don't want to go to the cash register and pay for something with 50 pennies, especially if I'm, yeah, somebody's being a jerk if they do that. You know, did you raid your kid's piggy bank or something to go to the...
I used to work at Speedway, and I had somebody come and get gas, and it was $20, and they paid with all pennies, nickels, and dimes. No.
Yeah, I'm sorry to hear that.
So on this one, couldn't you add the 50x and the 40x? Because they're the same variable.
Okay, Jessica's asking a really interesting question. Couldn't you just add the x terms together?
Because doesn't it technically become a two-step equation?
Well, I solved this like inequality. I guess that's what it's called. So I subtracted, to get the variable onto the left side, I subtracted 40x from 50x and came up with 10x equals 10. And then subtracted 60 from 100 and divided. So 100 minus 60 is 40, and then I just divided 10 from 40.
And you
So
got
I don't-
4?
And I got 4. So X
Okay.
equals, okay, so X equals 4. So now do I rewrite and solve again, or because we're trying to find X, Y, right?
Yeah,
Or,
but in your slope intercept form, when you plug a number in for X, it's going to generate the number for Y. So I'm
okay,
not sure I follow all the steps, but I think that you've done it correctly, because if you take that 4 and put it back in here in the first one, 50 times 4 is 200 plus 60, that gives you 260.
yeah.
Do the same thing with the other one. 40 times 4 is 160 plus 100. That's also 260. So at the point where both of these shops have worked 4 hours, the cost is going to be the same. But if it goes longer than 4 hours, who's going to pay? Which one's going to be cheaper?
Okay, yeah. Okay, so when X equals 0, is that right? Or when
No, I'm just taking the number that you solved for and plugging that back in. Not using 0. I got it.
Oh yeah. Okay.
You solved for X. You figured out what X is.
So what she said is you subtract 40 from 10 X.
I'll show you. It's not quite the way she described it to what I'm thinking about how she did it, but we'll get there.
How she did it. So the 40, and then she subtracted 12 and not 10X, and then subtracted the 160 from 100.
Okay, now you guys at home probably can't hear Jessica. What she's saying is to treat this like an elimination problem where you you subtract the second row from the first one. Okay, you can do that. You're going to end up with 0 equals 10x minus 40. Okay, well, you can't have nothing on the left side and everything on the right side. I'm still going to get 4. It's not quite the way Kathy described it, I don't think. Is this what you did, Kathy?
I did, no, I divided.
Okay, well, I'm going to end up dividing.
Yeah.
But I got to get some number on the left. I got to move that negative 40. What's Y minus Y?
Oh, okay.
These cancel. I can't just leave it blank. I got to put something in there. My 0 has now just become a placeholder. It's just holding the space until I plug something else in there. And so in order to get this constant to the other side, I got to add 40. So now 40 equals 10x. And I'm still going to get 4 equals x. Now I'm ready to divide by 10. It's a really terrible looking 0, but that is supposed to be a 0. And if I do it the substitution way, I'm going to end up basically at the same point as this. My substitution is set up right here. So I'm going to get the x terms together by subtracting 40x. There's my 10x. And I got to take 60 away. Those will cancel there. These will cancel here. And I still end up with 10x equals 40.
Okay, so that's what I did. That's how I solved it.
Okay. Either one of those ways is fine. The tricky part about using elimination when it's in slope intercept form is because of this. You end up with nothing y. And so you got to remember to put something there until you finish the rest of the calculation.
So, okay, so normally I would have put a 0 and then solved for X, but I think that's where I get, yeah. So I think I did both at the same time. So
Yeah.
I ended up, okay. All right.
So now that you know what X is, that's when you go back and substitute it into the originals and figure out what Y actually equals.
Okay, so in my mind, X equals 4, Y equals 0.
No,
Because
Y equals 260.
Okay, 260. Okay, so that's where I was wrong. Okay.
You know, in the middle of the problem here, you lose all of your Y values. So Y doesn't equal 0, it's 0Y.
Okay.
It's not the same thing.
Okay.
We can say that Y equals 0, but when we have 0 times Y, we just have 0.
Right.
And you could graph this too. And what it would look like, let's see, Y is 260. That's Y. X is 4, Y is 260. That 260 is up here. You have the other guy's shop going this way. So you end up with an equation where the guy that charges $40 an hour ends up being cheaper if the repair goes more than 4 hours, right? Because 40X is his hourly rate. It's $10 an hour cheaper than the other guy. If both of them take 4 hours, the cost is exactly equal. That's really was kind of the task that this problem assigned, if you will. If it goes longer than that, I want to go to the guy that's only charging 40 an hour. If it's less than that, I'll probably do the other guy because his diagnostic cost is less upfront.
Oh, the $60?
Yeah.
Yeah.
So good job, Kathy. You might end up liking these word problems after all, huh? Nah. See, I knew these questions were coming because I've used a slideshow before, but there's our equations that look like slope-intercept equations. The 260 is the cost for 4 hours from no matter which one that we use. Bob's going to be cheaper if it goes more than 4 hours because his hourly rate's less. Yeah, here's the graph I was trying to draw. I'm going the wrong way, I know. I knew that as soon as I drew it. But see, the red line is the one guy, his cheaper up until 4 hours. After that, he's more expensive.
Is this an example of a function graph?
Sure, absolutely.
Okay.
Any of these slope-intercept equations, any of these standard form equations, they're all functions because they'll pass the vertical line test, right? We can draw a line straight up and down. We're never going to cross the graph more than once. We don't have any repeating X values. Okay, so that's the last one of those word problems I want to do because it covers most of the typical examples. And this slideshow is in your materials. Let's see if I got the right link here. Yeah, system word problem, student version. So if you want to still work with that some more, check it out. Okay. Then there's also this handout in there. I'm not going to do this today. A lot of times I would do this as a, oh crap, it's a word It's Microsoft Word, I hate that. A lot of times I would do this as an assignment if we were all in class together, but we don't have the time. But you can see it's the same kind of problem. You got some tickets being sold, adults and children, or adults and students. You got the age difference problem. Then you got one of these coin problems. Whoever came up with these really likes those formats, because I've been here for 6 years and we've been using the same ones every year. Questions, anybody, before we go on to the next phase? And we are almost through then with this unit. Okay, got another slideshow. Graphing linear inequalities. This is where you need to bring your colored pencils. What the inequalities that we've done so far, there was an assignment for graphing inequalities, right? Single number line, one variable. Now we're talking about linear inequalities that go on to our XY graph. It's not one variable. It's not a one variable problem anymore. It's actually a line that gets graphed. And our answers are going to be either less than or greater than where that line is shown on the graph. We've got some new terminology. Linear inequality, that might be new. Half plane. Okay. I'll explain that in a minute. And boundary. When we were just graphing the standard slope-intercept equation, we knew automatically that every point on that line was a solution. We didn't have to worry about anything above or below the line. Well, now that we're talking about linear inequalities, now we do have to worry about not just the line, but what's above it and what's below it. Because now our definition of solution is expanding. It's gone beyond just one solution or no solution, etc. Now it includes entire areas of a graph. So this screen gives you some examples of some of those one variable inequalities like we did on that one assignment. X greater than 20, X less than 20, etc. Those would be easy to put on a single number line. But now we're talking about something that looks like slope-intercept, except now it's not an equation anymore, it's an inequality. It still follows that y equals mx plus b format, but now it could be greater than, could be less than, could be greater than or equal to, like this one, or less than or equal to. It's a linear inequality in two variables. So how do you know if a point like these are solutions? Well, you're going to have to do the substitution again, but now it's just not one number. We have a point here, x comma y, where we have an x value and a y value, so we can plug both of those into this inequality. So if y is -3 and x is -2, -2 times -2 is 4, plus 1 is 5. Is -3 less than 5? Yes, it is. Every negative number is less than any positive number. So now we're not just talking about whether or not things are equal. This is another interpretation situation, just like those single variable inequalities. You got to interpret your answer. What about this second example? X is 1, Y is -1. So I'm going to substitute the -1 here for Y. Substitute 1 for the X. So -2 times 1 is -2 plus 1 is -1. Is -1 less than -1? Nope.
Equal.
It's equal. So in that case, it's not a solution. Mathematically, you look at it and say, well, those are the same numbers, so they should be equal. Well, the sign in the problem, though, doesn't give us the choice of taking the equal value. It's got to be something for Y that is less than the rest of the calculation. So you really got to look hard at your answer to understand, okay, is this, what am I being asked to actually find? Are these true? But is it true in a different way than what we've been doing? It's not just does 3 plus 3 equals 6. Is 3 plus 3 less than 6? No. It's still 6, but a 6 is not less than 6. So it's kind of a mind game that you got to play with yourself to figure out, okay, what am I really trying to answer? And here's why. Here's what they look like. The graphing part of it is exactly the same. You start with the y-intercept. You use the slope to put another point on the graph. But now the line starts to look different. And you have to color an area of the graph in to show the relationship between the answers. So our inequality says y is less than -2x plus 1. Okay, well, here's 1. -2 slope means I'm going up 2, left 1, up 2, left 1. Now the dashed line becomes our boundary line. This red area that's colored in is what's called the half plane. Those vocabulary words from earlier. Half plane, because you're basically picking half of the graph as your solution area. The boundary is the line that we're graphing. And so now our line has a style. Less than or greater than would be a dashed line, because now this boundary is not included in the solutions. What? Because I'm starting with the boundary line here first. The boundary line is not included in the solutions because that's just the line that we graphed, but our answers have to be less than that. So if we go to the y-intercept, how do we know what's less than this line? Because all the answers that for y that are less than -2x plus 1, no matter what x is, are going to be below the line. That's what we have to color in. So if you're not sure about where the coloring should go to the y-intercept. On the y-axis, what happens when you go up along y? All the y values get larger. When you go down from the y-intercept, now you're in this colored area because all the y values are getting smaller. They're getting lower.
Is this the same concept as closed circle, open circle?
Yes, it is. Exactly right. That's a good way to tie those together. The open circle is your spot that's not included, and that's what the dashed line is. The closed circle would be a solid line if we have the equal to symbol also included. Very similar concept. And I don't know if you noticed or not, but these equations, these inequalities from the previous screen I was talking about are the same ones on this screen now with the graph. So where is this point -2, -3? Left 2, down 3, clearly in the middle of that colored area, that pink area. 1, -1. 1 over, down 1, it is right on the dashed line. Not included. The dashed line, if you're on that line, and it's a dashed line, it's not included, it's not a solution. So this adds another area of complexity, but this is the screen to pay attention to when you're doing these graphs. And this graphic is wrong. That's not a solid line. Who did that? There we go. Somebody changed my slide. There we go. That's what it should be. Greater than or less than, you're going to use a dashed line. If it has the equal to symbol underneath, either one of those, now you're going to do a solid line. Because that's exactly like having an equation. If you got the equal to symbol, it's still going to be a solid line. And the line that you're graphing, you're going to do it the same way as if it was an equation. But now you got to think, okay, what's the symbol that I'm using in the inequality, and does that require a dashed line or a solid line? So there's just more to think about. The shading, that's that half plane area. That's where you color in. Either one of these greater than or equal to, or just greater than, you're going to put the shading above your line. Whoa. Above the line for greater than. Remember, think about as you go up on the y-axis, the numbers get higher, so that's going to be greater than. You go down from the y-intercept, they're going to be lower, that's going to be less than. Back to the boundary line. So focus question 1 here. Y is less than x minus 3. For me, the first thing I do when I'm trying to graph these inequalities, I think about the line style before I even put the graph together. The main reason, honestly, is because I do everything in ink. And I don't like to try to erase stuff or scratch it out. It looks terrible. So I want to be sure in my mind that I know the right kind of line before I even do anything. So for this one, I don't think I can insert it on this. On this one, my slope is 1 because there's no number in front of x, but that means 1x. So m is 1. I go down here to -3 on the y-axis for my y-intercept, up 1, over 1. This dashed line is going to run upwards to the right, and my shading is going to be below it because it says less than. So on this next example, what's the line style going to be? What kind of a line am I drawing on my graph?
Dotted line.
On number 2?
Oh, no, it's going to be a solid line.
Solid line, right, there you go.
Equal to.
Yep. It's got that equal to symbol there. It's going to be a solid line. It's going to be less than or equal to. That one's going to be below the line also. Kind of going in this direction. Negative slope, up 9, left 4 from way down here. Fill it in over there.
So on a problem like this, on 9, so 4 is the x, and then 9, or well, -4 would be x, and then -9 minus -5, which is -14. That's the y change. No. Is that the delta y?
No. You don't. There's no calculation to do here. You have the slope.
Oh, okay.
It's 9 over 4.
Oh, yeah. Okay.
9 is the rise. 4 is the run.
Okay.
Your -5 is your starting point. Remember, that's the y-intercept. You don't have to worry about doing any
Oh,
calculation.
yeah, it's already solved. Okay.
Right.
Okay, yeah.
I mean, if you want to establish some points and do like a T-chart or a table,
Yeah.
and you can start putting in some numbers for X, you can definitely do that. But when you have the slope and the y-intercept already, you know, that you're just making more work for yourself. Just go to -5,
Okay.
go up 9, and it's got to go up to the left, so I'd have to go left and put a second point right there. You only need 2 points, right, for a line.
Yeah.
Solid line coming through, and then graph underneath there. Same, and we don't have time to really practice a lot with these today because I just wanted to introduce this because next week we have to deal with the systems of inequalities that puts all this together. But if you wanted to go into that inequalities section on your Google Classroom material and do some practicing, you could. Because here are some of these inequalities. And again, the answers are there. So, I mean, don't peek, don't cheat and look at the answers before you try it. If you really want to get something out of it, think about line style. Where does the shading go? You know, is this number 1, solid line? Yes. Number 2, solid line? Yes. Number 3, solid line? No. It's got to be a dashed line, and so on. So there's 12 graphs on there that you could practice with. A couple of them even are in standard form, so you have to do some converting. Give you some practice on that too. Questions? Anybody?
Did I graph this right so I know to go back and look at it? I know it's not perfect.
Yeah.
Okay.
Yep. Sure did. So that slideshow that we just looked at and that handout are both under this graphing linear inequalities. The next thing that I'll release here is this other section on systems of inequalities. And that will wrap up Unit 3. And so next week we'll have be able to do the test after Tuesday, most likely. And I've got a handout to post next week that will help if you want to do some extra work to get ready for the final. It's a final exam preparation packet. And we're almost done, ladies and gentlemen. And it'd be time to move on. All right? Algebra 1B. Yeah. So you can start graphing parabolas and do quadratic equations. Yeah, it's curves. Yeah, that look like a U shape. Yeah.
They get super confusing.
Yep. Do they open up or down or left or right or what's the deal? I'm going to turn off the recording right now and say, see you guys later. Thanks for being here.